Check, check. 1, 2. Can y'all hear me? Great. Okay, so I need one volunteer from the studio audience to get me a beer. Okay. No, can you see this? Can we dim the lights a little bit? It's gonna look like this the whole presentation. So if we can get the lights down, that would help out quite a bit. It's pretty bright in here. Yeah, keep going, like you mean it. Yeah, nice and dark. Yeah, we're all hackers here. Okay, is this coming to life? Can everybody see this okay? Yes, okay, great. Okay, so to start off, I have this lovely ASCII intro slide here. That's my company I work for. We're called Sysdig. If you've used Wireshark or the Sysdig command line tool before, you're probably very familiar with what we do. And below that is a new piece of open source software. It's free open source. Feel free to use it, and please, pull requests accepted. We need all the help we can get. So if you're interested in contributing, via Holden's talk earlier, please see me, see Holden. We'd love to get you involved. And we're going to do some low-level stuff today. But don't worry, I'm going to make it okay. Okay, so to get started, we're going to do a quick show of hands. You can see here on my screen, we have, and I might be able to zoom in, we can try. We have regular mode and we have rainbow mode. Show of hands, who wants regular mode? Show of hands, who wants rainbow mode? Okay, we're doing rainbow. Okay, so first let's try this really quick. And let's see what happened. Let's see if I can't zoom in, reset. I'm gonna try to zoom in one more time for folks. Let's see if I can't get away with this. And let's try rainbow mode one more time. Is that okay? Can we see that? Yep, great. So the name of this talk is Cloud Native Security. And I think I have 40 or 45 minutes today. So we're going to go by pretty quick. The first half is going to be slides that are going to look just like this. And the other half is going to be me literally hacking into a live Kubernetes cluster, running in a cloud provider. And we're going to look at how we would be able to use some of these open source tools to prevent someone like yours truly from hacking into a cluster. If you want to see the notes or the slides or learn more about me, you can take a picture. That's my GitHub. Please feel free to go and contribute to that repository because I am very busy. Okay, next. Let's talk about me, my favorite subject. Okay, so I wrote this book called Cloud Native Infrastructure. It's about infrastructure in cloud native environments. It's really just about using software to manage infrastructure in a cloud, which is how I got into Kubernetes and containers and everything we're going to be talking about today. I have a technical blog. It's called nivenly.com. You can see it up there. I've written blogs all over the internet. Like you could probably just type like something in my name and you might find something if you're lucky. I'm an ambassador for the CNCF, which is an organization under the Linux Foundation. I was just in Lyon, France, earlier this week doing a session there, very similar to the one I'm about to do here. I have stuff on GitHub. I've done a lot on GitHub, so if you're into open source software and things that work somewhat okay, feel free to check me out. A little bit about my background. So I started off contributing to Kubernetes a long time ago. I started contributing to Linux and FreeBSD. More importantly, Kubernetes has sort of been like the last 4 years of my life. I was one of the first maintainers of kops. I helped work on kubadmin. I wrote kubicorn one weekend. I contribute to Kubernetes, various parts, the API server, for instance. I've done some work with kubectl, and I started the cluster API project. Show of hands, who has heard of any of these tools before? Wow. Okay, so I'm preaching to the choir here. I've contributed to the Go standard library, Terraform. I just mentioned Falco, the Sysdig command line tool, and Wireshark. So I've been around and I've done some contributions in my time. And that's just kind of my background and why you should listen to things that I say. Okay, so like any good engineer, I want to start this discussion off today with a very well-crafted problem statement. How do I monitor my system in such a way that I cannot break it? How can I ensure that nothing can bypass this tooling? So the three subsections here are, do we want to begin auditing the network? And if so, how do we ensure that those two problems are addressed? Do we want to begin auditing the kernel? And how do we make the data coming out of either of these sources meaningful to humans? We've all seen TCP dump, who's used it? Who actually found it useful? I didn't. But if you know what you're doing, it can be a useful tool. But that's one of the problems that you see is it's really easy to get, not really easy, but it's more easy to get the data. It's much more challenging to actually make it meaningful and to make it tell a story, which is what I'm trying to do here today. A little bit of storytelling, a little bit of hacking, and I'm going to do my best to do this entire presentation from the command line. We're actually going to look at some real man pages. I might even write some C, like the C programming language. But there's a but here. My goal is to make this fun and easy to understand, regardless of your background in tech. In fact, I hope, and I've heard this in the past, that I can do this. There's one person here who has never even accessed a command line like the one we're looking at now, and actually will walk away from the talk with valuable lessons. So that's my challenge for myself. And I hope to get feedback from all of you afterwards to see if I succeeded in my goal. OK, so again, I'm going to do the Scrum Master thing here. We have an agenda. So the first bit on our agenda is we're going to look at understanding containers. So I want to get an idea of who I'm talking to today. Who here has ran a container? Who here has built, keep your hands up, who here has built a container from scratch using the C programming language? Nice, nice, my people. Nice. We got 3 right here. This is the C kids group. This is like, it's like the lunchroom. Like these are the people who rate C. OK, so in order to understand this, we're going to, again, make this really simple. We're going to go over 3 basic concepts here: C groups, namespaces, and clone. If you have heard of one inclusive or more of these, raise your hand. Great, awesome. OK, we'll do a quick review. And then we're going to look at, after we've learned these concepts, how we can use tools like writing a kernel module or this new hotness eBPF, and this tool Falco, which is an open source tool that's hosted by the CNCF, which is part of the Linux Foundation, to understand how we would, 1, break a system, and then 2, how we would able to not only track that and tell a story from that, but potentially prevent it later. And that's what we're going to do today. And this is relevant for anyone who's running in Kubernetes. Right, let's do this the other way. Who's not running in Kubernetes? Right now. OK, awesome. So this is good. This is really good, because this means I'm going to be able to scare you before you start running. Right? That's what we want. OK. OK, so let's look at C groups. So C groups is short for this thing called a control group. And I'm going to start off, and I'm going to kind of, I want to like, can I angle this, actually? Yeah, there we go. I'm going to start off, and I'm just going to kind of rant about C groups here for a second, in the hopes of telling you, in my own words, what they mean, so that you can understand exactly what it sounds like without going into all of this kernel riffraff. So basically, in a computer system, you would have a process. Like everything that you do on a computer system like Linux would have a unique process ID called a PID. And a C group is a way of grouping these processes together and putting boundaries on them. Probably the simplest way you can imagine this is if I was to create a C group, let's say we called it Amsterdam, and I wanted to put a limit on the amount of memory a process could use that was in the Amsterdam C group, and you started a process that took 1 byte more in memory than I had declared, the kernel would shut you down. The kernel would terminate that process. And that's all a C group is it's just a way of grouping together, just like you would in a database or you would in a file system, of grouping things together and defining arbitrary limits for them. So I could do a quick demo where I write a bash program and I make it sleep for 1,000 seconds and like stick something in memory, and then I'll set my C group boundary to 1 byte. Naturally, that process is going to exceed 1 byte, and the kernel would shut it down. Pretty simple, except for if you look here, on the screen, there's some sort of example bash commands how you would start actually adding processes to a C group. You can look in the bottom half, this big chunk of rainbow text down here. You can see the folders that we have defined. Block I/O, this is storage. How much storage can a process use? We have memory. How much memory can a process use? We have freezer. We have devices. We have CPU. How many cores can I use? How many cores can I not use? We can start to go in and define all of these things. And this is handy because this is a new feature in a Linux kernel. Because before, you were bounded by whatever the system had. And this basically allows us to synthesize or spoof what we want the process to believe is true. We are literally telling a process to imagine a computer and respect that computer. And regardless of what computer it's actually running on, according to the process, this is what you got. OK, everybody good on C groups? Great. OK, next, we have namespaces. And now these are relevant because these need to behave almost identical to C groups, but there's a very fundamental difference. A C group tells you the limit of what you can or cannot do. Right? How many bytes can I use? How many cores can I use? Whereas a namespace is more of a communication boundary. How do the processes intercommunicate? What can one process see from another process? So a little bit of history, if you're not familiar with how the kernel works. Whenever a computer starts, you get this magical PID. It's called PID 1. And it's sort of like the equivalent of the Big Bang of your computer booting up. It's where everything starts from. And if I was to isolate a new process away from that original PID, this newly created process would basically be like a universe within a universe, right? It would think it is the PID 1 and the only PID 1 in existence. And then that PID could create a PID 1, and that PID could create a PID 1, and we could go and we could do this recursively until we either put our system in deadlock or we get too bored and we stop trying to do it. So namespaces allow you to isolate different parts of your system. So now, as a Linux server administrator, like I can see somebody like walking up to a computer, like I'm going to put you in a C group, and I'm going to use namespaces to tell you what you can and can't do. But you can see, as a savvy computer user, you would be able to potentially control, let's say, Nginx, let's say a JavaScript program, let's say a C program, let's say Docker, let's say Kubernetes, let's say MongoDB. How much storage can it have? What other types of processes on the system can it talk to? What other processes on the system can it even acknowledge or even realize that they are actually there? And so now we can start to govern this on a Linux system. Everybody good on namespaces? Groovy. Real quick, while we're on this slide, if you look, we have network, mount, PID, user. Let's go back to C groups. What do we have here? CPU, PIDs, network. You can see that there's similarities, and these are what we call Linux subsystems. These are how we break down the Linux kernel. And if you look at a computer, really there's three main big ones: disk, memory, compute. And with those three things, you basically can build a computer. OK, so now that we have these ideas of how we can control processes, what they can and can't do, and who they can and can't see or communicate with, we can now start to design tools to allow us to start processes giving these new constraints, giving these new boundaries. So this is relatively recent in kernel years, which that's like the reverse of dog years. Like one kernel year is like 7 human years. We have this new processee here called, or this new syscall here called clone. And clone is familiar with fork. We all know fork? Yes? Yes, fork? OK. But the big difference with clone is when you clone a process, you can tell it which namespaces you would like to share with the cloner. So we have two processes after we execute clone successfully. Let's call the first one that we started with the parent, and we'll call the next one the child. And if I was to share all namespaces with the child, it would effectively be identical to fork. The child would have access to all of the same system space that the parent had access to. And that's how fork behaved, and that's how we built Linux, and that's how we built Bash, and that's how most of computers have worked throughout the broader history of computer science. But now we have clone, and clone says, OK, I am a parent. I would like to create a child, but I only want you to see PID 1. Or I don't want you to see PID 1. Or I don't want you to have the same network as me. So if you've ever exec'd into a Docker container before, you've noticed that it's somehow magically running on your system, but it has its own root directory, and it has its own processes, and it basically behaves like a very lightweight small computer. And we're able to do that using clone, C groups, and namespaces. And that's how containers work. Now, let's go a step lower into the kernel. So here's the kernel that's respecting all of these new primitives, and it's baked into the kernel that it respects it. And now we have what we call user land, this magical place up on top where we get to send commands down into the kernel and they come back up with some sort of response. And that is effectively how everything you do on a computer works, whether you're looking at Facebook or you are hacking into a bank. it's ultimately going to have to go through some abstraction layer on top of hardware, and it's going to go through some kernel or some spoofed kernel along the way. So that's clone. And there's many others. There's clone, there's unshare, there's mount namespace. There's a lot of other commands, but this is the one we're going to be looking at today because I think seeing it create something is really going to be a powerful exercise for us. OK, so we're going to look at some C code, but don't panic. This is just the same function 3 different times with slightly different arguments. And this is just going to demonstrate concretely how you, as a C programmer, would be able to create a new process with different namespaces. So if we look up here, the first example, the one that's uncommented up here, it says int pid equals clone, fn pchild stack, 1024 squared, and then right there in all caps we see sig child. Okay, so sig child is the first flag that we pass in this example. And what do we think sig child does? It sends a signal. Well, it's not a signal, but we represent it as a signal to tell clone to simply create a new child, just like fork. Now let's move on to a slightly more involved example below. In this example, we have clone new pid and clone new child. So in the second example, we are gracious enough programmers to share the PID namespace with the child. So a PID namespace, again, remember everything has PID1 to start, and then some number of other PIDs moving forward for every process. If we were to execute the second command, we would be effectively blind to anything running on the host system. And this is why, when you're in a Docker container, if you list all the active processes, you only see 3 or 4. But if you go to your host and you list all the active processes, you see hundreds, right? So using C, we're effectively able to control what system resources we share with other parts of these newly created child processes. And of course, the last example you see here, we have a very long, we're very, very gracious in this example. We're going to give them access to almost nothing. They get a brand new PID, a brand new network, a brand new namespace, and we're going to create a new process with sigchild. OK, so we're going to actually execute some C code, and we're going to run this bottom one here in just a moment. And what we're going to do is every time you use the clone function in C, you pass in what's known as a function pointer, or effectively you say, go run this other instruction set in this new process. In this case, the instruction set we're going to run, it's a really simple program. It's called bash. And we're just going to create a new bash shell, and we're going to run it in this new example. OK, so before we jump into my terminal, let's do a quick review. Everything we just talked about, that last clone example, is effectively creating what we in computer science call a container. That's all a container is. And I can write a container in about 100 lines of C. And that is enabled by 2 kernel features, namespaces, and C groups. Containers can be built in a small amount of code. So we're going to look in just a moment. All we really need to do is run bash inside of a clone function. And we've created a brand new bash shell that we have a TTY in, and we can do whatever we want, but it's constrained to the namespaces that we gifted it when it was created. And last but not least, container runtimes, which implicitly means Kubernetes, abstracts all of these scary kernel things away in an effort to make it easier. So like 4 years ago, when I first started talking about Kubernetes, one of the things I used to get on stage and say is, Kubernetes makes it easy for you to run your applications at scale. And that was true. It did simplify things, believe it or not, for many folks, because it standardizes things. So Kubernetes has grown. Containers have grown. The environment, the ecosystem has grown. And now we're at a place where we have people, and I'm going to quote Jurassic Park here. Has anybody seen Jurassic Park? It's my favorite movie. Yeah, like you were too busy thinking whether or not you could. Nobody stopped to think if you should. And basically what people are doing is they're given a lot of power. And they don't realize the power that they have, and they get themselves into vulnerable situations because they don't understand how a small bit of YAML that says run this JavaScript image, or run this PHP image, or run this Python image, can actually expose you to super serious kernel vulnerabilities using these primitives here. So granted, it does make it easy for you, it also can make it very vulnerable for you. And so that's why I decided to get into security, and that's why I've been working in the kernel and working on these open source tools over the past few months. So to get started, we're going to create a container. We're then going to run a Docker container. We're then going to run a container in Kubernetes. And we're going to watch as Falco, a command line tool, detects all three of these identically. Because according to the kernel, it doesn't matter what you're running in because you're just a normal process. And then we're going to look at how, in a situation like Kubernetes, securing that is almost impossible to do from user land because of this isolation. It's impossible for, like we just got done describing, through a namespace to go from one to the other. So in a weird way, you could potentially block yourself out of securing an application. But we go a step further and we go into the kernel and bring that back up. So if you want to see what's truly going on in your system, regardless of how you're running a container, the only way to get a true story and a true source of truth is to go from the kernel. And with Falco, we're able to take that, and we're able to actually tell a story and make sense of it. OK, so who wants to see us first run some containers and then hack into Kubernetes? I know I do. Let's do this. OK, so first things first, I can actually why is this not zooming in? Oh, Icelandic keyboard. OK, is that better? Can everybody see that? A little bit easier? OK, cool. So here we have a simple C file called container.c. We're going to open this up in my favorite text editor. OK, so here we're going to look at some C code. And really all I want you to see is two things, and the rest is just kind of like memory management. And like you'll recognize it if you write C, but it's not super important for the demo. Here you see int fn, which is a function. And then we see system bash. And all we're doing is we're running bash, right? And if we scroll down further in the file, you can see here where we have clone calls. This is what we looked at just a moment ago in my terminal. And in this last one, we're going to clone bash in C using these namespace SIGs and these namespace flags. So let's do it. So we'll close out of Emacs, and we will compile our code. And we're going to call it, I'll be lazy, I'll call it container. OK, so you see here we now run container. So if you looked at the flags and you know the Linux kernel very well, you would know if I tried to run this as my current user, Nova, it's not going to let me. I got a -1 error, unable to create the child process. And the reason for this is in order for us to create a new PID namespace, we have to have access to the first PID namespace, which basically means root on a system. So in order for you to take control of the system, you first have to escalate to root. So in order to make this code actually work, sudo bang bang, the name of my band in college. OK, so I echoed out some output here just to demonstrate a few things. And then if you notice, at the bottom, it's red, and at the top, it's green. And that's because my bash RC for both of these is smart enough to know if I'm a root user or an unprivileged user. When it's red, that's scary mode, you're root. And when it's green, it's safe mode, you're not root. But more importantly, up at the top, in that original C program, you see we were on number 29,730 of our process ID. Meaning there was about 29 or 30,000 other processes running on my computer, maybe some clocks, maybe Google Chrome, maybe Emacs, maybe my text messengers, like whatever. And in this newly created process that we have here at the bottom, it thinks it's PID1. For instance, I have access to the original PID1 from here because I shared it, right? But if I IPA, which I did not share this namespace, you can see here that we only have 2 interfaces, right? So if I close this, go back, and I run the same command again, you can see all the interfaces on my host computer. So we've effectively demonstrated how you can start to literally build a process that thinks the world is different than it actually is in C. And so if I was to do this, let's go back, and we're going to run our container again. And now we're in bash down here. I'm going to clear my screen. I'm going to run this experiment. So somebody shout out a funny word. Puppies, kitties. Cheeseburger. OK, we're going to do cheeseburger. OK, so I'm going to touch, or we all know this command, create a file. And it's going to say user local bin cheeseburger. And before we do that, we're going to open up a new shell. And we're going to run this program called Falco, which you can go and you can download it from GitHub. And I'm going to clear the screen here so we can all start. Actually, I'm going to make this a little bit easier to read. Sometimes Chrome likes to be noisy and do scary things, so I'm going to grep -v or ignore anything that contains the string Chrome. So we'll do this. We'll clear our screen. So anything I do on the system moving forward, if Falco considers it hazardous, we should be able to start to tell a story here. So going back to our container that we're running in, we're going to touch user local bin cheeseburger. No big deal. Now let's go back to Falco. And you can see here, from the kernel's perspective, it was able to say, error, a file below a monitored directory was opened for writing. And you can see that we were able to actually parse syscall information from the kernel, not from userland, to create an alert to let us know something malicious happened. And if I exit out of this, the instance of everything I did, the bash history, everything is now effectively gone forever. Which means if you walked away from your computer at lunchtime and I was smart, I could have dropped this binary off, executed this command, put it in a keylogger, catted out all your Etsy shadow information, stolen all your credit card numbers, gotten your Google Chrome password, and then exited out of it and walked away. And without a tool like this that can actually understand what's happening at the kernel level, you would potentially be able to write software pretty easily to do some pretty scary things on a computer. So let's actually run a Docker container. We've all ran Docker containers before, right? Yeah, OK. So in this example, we're going to come here, and I'm going to Docker run interactive TTY so we can perform the same experiment again. Docker run IT, we're going to run Nginx, which this is one of the most commonly, probably most popular downloaded Docker image on the internet today. And we're going to do everybody's favorite good old bash, again, just like we did in the first example. So here we are, but this time we're in a Docker container. And Docker obviously is a little bit more complicated than 100 lines of C that I wrote a couple hours before I walked on stage. This has been a project that's been around for a very long time. So now let's touch user local bin cheeseburger. Now bear in mind, Falco's running on the host system, and I'm running in a container now. If we go back to Falco, you can see not only did it detect that shell history has been deleted or renamed. This was when I exited out of that C program earlier. But we also have notice a shell was spawned in a container, which if a shell is spawned in a container, that's pretty alarming as well, because that means whatever you're doing, you could potentially cover up if you knew how to manipulate the system. And then we get the exact same response that we got when we ran it in the container I had running in C. So from the kernel's perspective, the way the kernel works, it doesn't matter if you're running in your own homegrown container or a Docker container or any container. The kernel still interprets everything you do identically using these things called syscalls. And a syscall is basically the input and output of the kernel. And that clone function we looked at earlier is an example of one of the syscalls that are available on every Linux kernel. So let's take this a step further. We're going to run this in Kubernetes. In fact, if I list pods in Kubernetes, I'm in the default namespace. I have my system configured as a user who can schedule what Kubernetes calls a privileged container in the default namespace. Now, what I'm about to do is, I'm not going to show you the code because that's ethically not probably the best idea. But I'm actually going to, I'm going to run a container that's privileged in Kubernetes. And in order to do this, all I had to do was change a 0 to a 1 in some YAML. And I can show you that if you want to see that. And I'm going to run a container. And that container, I specifically designed to audit all of the available namespaces and mount everything it can and basically build a bash shell from scratch. And I call that function scary. And so how we do this is we are going to, and I can't take all the credit for this. The original idea from this came from one of my old colleagues at VMware and another friend. They did a presentation at DEF CON. If you get a chance to go check it out. I took a lot of their work and kind of took it a step further. And I used that at a demo at a Linux presentation earlier this week. So we're going to grab a host name of a node. So this is a server. This is not a pod name. This is not a container. This is a server running in, well, if you don't know where that's running, ask somebody else. I'm sure they'll be able to tell you. So we're going to run this again. And we're going to paste in an argument, which is just going to be the C name that is publicly resolvable. You could pull out your phone and go to this right now and actually hit this URL. And it's going to do a little bit of magic. Bam. So this doesn't look like much. From the default namespace in Kubernetes, I have now gained root access of the underlying host in a container. So if you don't believe me, if you ever go on a Kubernetes computer, so imagine I had like a server right here that was running Kubernetes, and I scheduled 10 PHP programs. Those 10 PHP programs would be running in 10 containers, right? Right? Makes sense? Imagine being able to create one of those containers and then taking over the entire server. To demonstrate, this Kubernetes cluster happens to be running a well-known command called Docker. And if I do a Docker PS inside of a container, I can now see every container running on the underlying Kubernetes system from the default namespace because of the way that this user haphazardly exposed C groups and namespaces to the containers running on that system. So this is pretty terrifying. If you're running Kubernetes, this is something you probably should be aware of. So what's cool about this is even if one of my users deployed one of these programs, like the one we see on the screen right now, because I have Falco running in Kubernetes, just like it was running on my laptop, I'm able to see all of this and tell the story. So check this out. So now we're going to do this command called klogs, and we're going to run it in the Falco namespace, which this is a Kubernetes namespace, not a Linux namespace. I know, don't ask me. It's computer science has to make everything complicated for some reason. But we're going to do klogs in Falco, -L, app is equal to Falco, -F. Oh, yeah. OK, so let's do this. I'm going to ignore some of this stuff to make it a little bit easier for folks since we're zoomed in so far. OK, capital K. OK, great. So let's find it. Here we go. Right there. 16:15. What time is it right now? 16:17. So about 2 minutes ago, in Amazon, in America, Falco was running in Kubernetes and detected that somebody did something in the default namespace. And we could actually, if we really wanted to expand this, we could get rid of that V, and we can actually get more data here. Let's scroll up and let's try to find it. 14:16, 14:15. Here we go. Again, I think we might have actually exhausted these logs. It's moving pretty quick already, and there's only about a 3 or 4 minute retention policy here. But the idea here is that you would be able to begin to start to understand what's happening at the kernel and putting these logs together. And you're like, OK, Nova, this is cool and all, but like at the very beginning of your talk, you talked about how Wireshark and TCP dump is hard to use and nobody wants to use it. The beauty of Falco is it's completely extensible, so you could plug this in anywhere you want. There's a server on the other end, and if you could speak HTTP or gRPC, you can take any action you want arbitrarily. So anyway, this is both a warning and a caution to anyone looking to get involved with Kubernetes that security is a huge concern that you ought to be starting to think about. And in order for you to have a truly secure system, you need to start understanding some of these low-level primitives, even if an abstraction like Kubernetes or like Docker makes it easy for you. Otherwise, you're liable to run into situations like this, where somebody is doing something and you would have virtually no way of knowing about it. So yes, security is a concern. Yes, there are ways that if you know what you're doing, you can easily take advantage of people who don't know what they're doing, and that's pretty much all hacking is. But thankfully, there's nice people in the open source and Kubernetes community who have come together to start looking at how we solve security as a community, and that's what we're looking at here on the screen. So if anybody has any questions, I'm happy to answer questions. If anybody wants to see any of this code, I'm happy to share the code. At the beginning of my talk, I gave the GitHub link. If you want to see it, stick your hand up in the air, and I'll put it back up on the screen. Yeah, let me put it back up on the screen for you. We have one over here. So let's see here. One. Where are we? Change directory, Keynote, MDP 1deck.md. Scroll down. Scroll down again. There you go. So you can grab a photo of that, all the code. I don't think I've pushed it yet today, but I'll push it here in the next hour or so if it's not there. But I've given this talk 100 times, so there should be plenty of examples there. But feel free to go there and check it out. And yeah, that's my story. That's my spiel. I've been working on Kubernetes. It's great, but it's also vulnerable if you don't know what you're doing, and you should take security seriously. Thanks for coming to my talk. Yeah, sure. I don't know.
Well, if anybody has questions for Nova?
I like when nobody asks a question, because then I get to say, OK, you had your chance. Nobody gets to come up to me afterwards and ask questions. That was a joke. Come on, I'm killing it up here.
You can throw it, Nova.
Yeah, where? Yeah, right here.
Do I have to wait for the microphone? This is a microphone?
Yeah.
Amazing. I was wondering, do you fix this by not running privileged containers?
So the reason I showed this exploit was because you see privileged containers all over Kubernetes. So it's if you're into InfoSec, if you're into security, this is a well-known bug. Or not bug, rather, but well-known exploit or attack vector, as we like to say. But you would potentially fix this on your end by doing some sort of auditing to make sure that folks aren't deploying containers with these configuration options set. The whole point of the demo here is that it's not always possible, and there's always new exploits coming out. But if we're gathering every syscall that's going into and out of our system, we would ultimately be able to piece it back together and tell a story later. And that's kind of the takeaway here. And what you do with Falco after you detect something is, I mean, again, it's arbitrary. It's up to you. If you want to stick it in a log file or you want to have it call your home phone, you can have it do whatever.
Nice.
Yeah.
Any more questions? No? OK. So thanks again, Nova.